Hey guys, welcome to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 7, Quantum Mechanics. Number 1, Louis de Broglie correctly postulated that matter has wave-like properties. What was the de Broglie wavelength of a baseball thrown at 95 miles per hour? Okay, so the difference between the wave-like properties that we're dealing with now, and the waves that we've been dealing with before, is that this has mass. Okay, photons, which have the characteristic frequencies and wavelengths that we've been talking about, photons do not have mass. No mass. They are massless particles. Okay, so the difference here is that we're now talking about things that have mass, and that these objects are producing different wavelengths. Okay, and so anything that's actually has mass and is moving is going to have a de Broglie wavelength, and the way that we represent that mathematically is through the de Broglie equation that looks like this. This is Planck's constant divided by mass times velocity. Okay, so that becomes 6.626 times 10 to the negative 34 joule seconds, and then that's over 0.142 kilograms times 42.5 meters per second. Some people ask, what unit does the mass have to be in? It has to be in kilograms, because 1 joule is equal to 1 kilogram meters squared per second squared. Now, a lot of people kind of confuse that by that. It comes from the characteristic, or the iconic equation, E is equal to mc squared, where we get mass. So this is energy is equal to mass times the speed of light squared. So mass is in kilograms times meters per second, and then that's squared. And that ends up being what we call the joule. Okay, so that's why we need to use kilograms, because ultimately they'll cancel out using the math correctly. Now, if you do the math correctly in your calculator, you should get about 1.10 using sig figs times 10 to the negative 34 meters. And that would be the wavelength, de Broglie wavelength. All right, number 2, calculate the wavelength of the following objects. Okay, wavelengths of the following objects. Notice they didn't say of, some particular photon or particular wave of, they didn't give you any frequencies, right? So we're not dealing with the speed of light or anything like that here. So we're using the de Broglie equation again. Planck's constant divided by momentum. So I've got a muon, a subatomic particle with a mass of that, traveling at a certain speed. So notice that there'll always be objects with mass moving. A mass that is moving, a mass that is moving, okay? And that's going to be the characteristic of de Broglie wavelengths. So here I get 6.626 times 10 to the negative 34 joule seconds over 1.884 times 10 to the negative 28 kilograms times 400 meters per second squared, or 400 meters per second, excuse me, okay? If you do that correctly, if you plug that into your calculator correctly, you should get 8.79 times 10 to the negative 9th meters. Okay? So, part B here, we've got the same idea. We've got mass that's moving. We've got 6.626 times 10 to the negative 34 joule seconds over 9.11 times 10 to the negative 31 kilograms, 5 times 10 to the 6th meters per second. Okay? If you do that correctly, you should get about 1.45 times 10 to the negative 10th meters. Okay? And then lastly, part C, we've got an 85 kilogram sprinter running at 8.5 meters per second. So H over mv is equal to 6.626 times 10 to the negative 34 joule seconds over 85 kilograms times 8.5 meters per second. Okay? And you should get about 9.17 times 10 to the negative 37 meters. Okay? Notice that our wavelength gets smaller as the mass increases, right? Because the bigger this is on the bottom, in theory, the smaller the wavelength should be, okay? So that's kind of how you'll want to solve questions like this. You'll always notice that if they ask for a wavelength, sometimes they won't say de Broglie wavelength, but if they say calculate the wavelength of an object, something with mass, you're always going to use this equation, okay? Number 3, a synchrotron is a type of particle accelerator in which a ring of variable electric and magnetic fields accelerates particles to speeds nearing the speed of light. The largest synchrotron in the world is the Large Hadron Collider in Geneva, Switzerland, where protons can be accelerated to speeds up to that speed times the speed of light. Okay, so pretty much 99.99999% of the speed of light. Okay, what is the de Broglie wavelength of one of these protons? Okay, so the proton must have mass, so here's the mass. What speed are they moving at? This speed. So I know that my handy equation, I got h over mv, and in this case I'm going to say 6.626 times 10 to the negative 34 joules seconds over and I'd say 1.6726 times 10 to the negative 27 kilograms, times the velocity, which is going to be 0.999 and then 99991, times the speed of light, which in this case I'll just use 3 times 10 to the 8th meters per second. Okay, if you do that correctly, you should get somewhere in the ballpark of 1.32, 1 times 10 to the negative 15th meters. Okay, now they want to know that same thing with an electron now. So in part B, we'll say 6.626 times 10 to the negative 34 joules seconds over, and in this case, 9.11 times 10 to the negative 31 kilograms, then times the same speed, right? So 0.9999, 3 times 10 to the 8th meters per second. Okay? And if you do that correctly, you should get somewhere in the ballpark of 2.426 times 10 to the negative 12th meters. Now, lastly, letter C. If the relative uncertainty in the velocity of a proton in the Large Hadron Collider is 5%, what is the uncertainty in its position? Okay, so now we're dealing with uncertainty, which has to do with Heisenberg's uncertainty principle, and there's an equation that goes along with that. And then they're asking us, how does the uncertainty affect the ability of scientists to collide that proton? So we're throwing a proton at an atom or another proton, okay, in the Large Hadron Collider. So first you need to know the Heisenberg uncertainty principle equation. So we've got delta x, which is the uncertainty in position, okay, times mass times the uncertainty in velocity. So uncertainty in velocity, I'll just put un in velocity. Okay, and that's greater than or equal to Planck's constant over 4 pi. Okay, so they tell us that the uncertainty in the velocity is 5%, meaning that using the speed here, this speed here, we only know that somewhere within 5% of that is where the actual velocity is. Okay, and so the uncertainty, that this delta v is not the actual velocity. We're not plugging in 0.99999% of the speed of light again. We're actually plugging in that value times 5%. Okay, so in this case, we have to divide over, use our algebra to move that over. Okay, so I'm going to move it over, divide by m delta v, so that becomes times m delta v. Okay, and then I get the following. Delta x, which is what we're looking for, is greater than or equal to Planck's constant all over 4 pi times m delta v. Okay, now let's plug in the numbers that we know. So we got delta x, the uncertainty in position, greater than or equal to Planck's constant. So I'm going to say 6.626 times 10 to the negative 34 joules seconds over, we know 4 pi is just a constant. Then we got mass of what? Mass of the proton, right? And we knew that the proton from a previous question was 1.6726 times 10 to the negative, was it 27? 27 kilograms. Okay. And then that's times, I'm going to have to put some extra space here. So in this case, we got to put 0.05, which is the 5%, times, and then we'll say, continuing down here, 0.9999, this whole value here, times the speed of light, which I'll just put as 3 times 10 to the 8th. And then again, okay, so we'll just put brackets around this part here. Okay, so that's a lot of math. A lot of people will actually mess up in the calculation portion of this. So make sure that it's this Planck's constant all over 4 pi times 1.6726 times 10 to the negative 27 times 0.05 times this value, 0.9999, times the speed of light, 3 times 10 to the 8th. Okay, if you do this correctly using the values that I've given you in this problem, okay, you should get about 2.103 times 10 to the negative 15th meters. Okay, so that answers one part. Now, what does that mean? In interpreting this, this is now the uncertainty in the position. So somewhere around the radius of a proton, oops, I don't know where that came from. Somewhere in the radius of a proton, okay, so out here, in this case 2.010, and I'm going to put this into femtometers, which is FM. Okay, so FM is times 10 to the negative 15th. That's equal to 1 femtometer. Okay, so I'm going to put 2.103 femtometers. Okay, and what is the radius of the proton? Well, the radius of the proton is 0.9 femtometers. Okay, so this right here is 0.9 0.9 femtometers. So this whole region around the proton, is the uncertainty in the position. So I don't really know exactly where in the circle the proton will be, but I know it's going to be at least within the circle, because that's where I'm uncertain. Okay, and so we have this kind of big sphere almost when we're throwing a proton at an atom. We're trying to see, is it going to hit the atom? Now, the only way to do that is to compare it to the actual radius of the atom. Okay, so here's the radius of the atom, which is 1 times 10 to the negative 10th, which, if you notice, 10 times 10 to the negative 10th compared to 10 times 10 to the negative 15th, that's almost 10,000 times larger. Okay, the atom is about 10,000 times larger than the proton that we're throwing at it. So it's actually relatively easy to determine if we're going to be able to hit the atom with the proton in this Hadron Collider. So what I would say is, it's kind of like throwing a baseball at a house. So a baseball, we'll say this is a baseball at a house. Okay, it's kind of hard to miss the house. I haven't really drawn the house to scale here, right? But it's hard to miss, right? You're going to hit some point of the house. You don't know exactly what, but you're going to hit it because it's pretty large. It's hard to miss it when you're throwing it right in the direction of the house. So we'll say easily hits atom, okay, for one of the answers. But when we're trying to hit it with another proton, right, here they've asked us for see if it can hit an atom or another proton. It's like throwing a baseball at another baseball. It's kind of difficult, right? So we would say it's probably more difficult. We'll just say more difficult to hit another baseball. Okay. So that's kind of how you want to think about the uncertainty principle. Just realize that we're never going to know exactly where something is if we have the velocity, or vice versa. If we have the position relatively, we're not going to really know its velocity either. It's just kind of how it works as far as the subatomic particles go, especially protons and electrons. Okay. All right. Number 4. What do wave functions tell you? Okay. Wave functions are solutions. I'll just put equals solutions to the Schrodinger equation. Okay. Now, don't freak out. The Schrodinger equation is an equation that we use to solve for energies in an atom, energy levels in an atom. So I'll just put solving energy levels in an atom. And honestly, if we were to just look at the equation, it looks really complicated. And so you're never expected to use it or know it. In fact, we usually use supercomputers to solve it, because it is pretty complicated, especially when you start talking about really big molecules. So solving energy levels in an atom. So the wave function, what the wave function tells you is the allowed energy. So it tells, or shows, I should just say, shows allowed energies in an atom. Okay, energies in an atom. Okay, they don't describe the path, so don't describe any path. There's no like orbit. Okay, it's just describing a particular energy around the atom. So if you remember, particularly in Bohr's model, we had n equals 1. That was technically one energy level, right? And then n equals 2 was in a higher energy level. Remember, we would calculate those energy levels using this e squared negative RHC over n squared, right? What we were doing here is calculating the energy of those levels, and you'll notice that as you increased the n number, this number got more negative, which means it got technically more. It had higher energies. Okay, so each consequent n shell had increasing energy levels. So that's what wave functions tell us. They tell us energy levels around an atom. So following that, in part B, what are quantum numbers and how are they related to the wave function? Quantum numbers, I'll just put Q numbers, are the components of the wave function. Okay, so they come out, there are particularly 3 integers that come out in the wave function that we deal with. So a wave function. Principally the n, the l, and the m sub l. Okay, this is the principal quantum number, the angular, and the magnetic quantum numbers. Okay, you don't need to know that yet. We'll do that in the next part, in part 2 of this problem set. But these integers, so these integers here, integers are the wave or the quantum numbers. Okay, So these three components of the solution of the wave function are what tell us the actual energies. Okay, remember I was talking about n equals 1? That's what n is, okay? N is talking about the shells, okay? So part C says, what does the square of the wave function tell you? So wave function squared, so psi squared. What does that tell you? What it tells you is where you can find the electron 90% of the time given particular quantum numbers. So given particular quantum numbers, it will tell you where you can find the electron 90% of the time. Okay, in a given 3D space. So what they've done to measure that, to kind of explain why we say it this way, is they'll make a diagram and then they'll calculate it, they'll do their best to figure out the position. Remember, we can't always know it specifically, but for example, we have one of those shapes that comes out in the wave function squared is a sphere. We call it an s orbital. And we'll get to orbitals here in a second, but why the reason that we get this shape is because we find that 90% of the time we find the electron within this region of space, in this sphere, okay, in this sphere. And let's say the nucleus is right here. Here's the nucleus, okay, and around it is this cloud of where the electron could be based off of these quantum numbers. These quantum numbers are telling us that it should be in this space, and the wave function squared is saying in this 3D space is where we should find it, the electron 90% of the time. Okay, 10% of the time it'll pop out of this region. Okay, but 90% of the time it's always going to be found within this region. And we have different shapes. I've just shown you one of them, which is a sphere, and I'll show you what the other ones are later. Okay, but that's what you want to know what the wave function squared is. It just tells you where you can find the electron 90% of the time in a given 3D space. Okay, so that given 3D space is actually what we call an orbital. So I'll just say the given 3D space that we calculated from here. Okay, so this is an orbital. Okay, and it's kind of like it's a cloud. I'll just say a cloud of where we can find the electron. Okay, and it differs from orbits, which we'll get to here in a little bit in the next part of the video, in that it's just a cloud. There's no designated path for this electron to travel on. Okay, it's kind of just in this region where we think it could be 90% of the time. Okay. All right, well, I hope that was helpful for part 1. I'll see you in part 2.